Hello, this is Dr. Ayesha Butalia. Namaste. I welcome you all for today's session for the subject Database Management System for the topic Transactions. We are going to take the following presentation on the topic Transactions. So the outline of the lecture for transaction is transaction concept, its state, concurrent executions, serializability, recoverability, implementation of isolation, and its terms in SQL and its testing. What is transaction? Basically, a transaction is a unit of program execution that accesses and possibly updates various data items. So basically, it is a set of instructions. So this 1 to 6 given here in the example is the set of instructions, and it completes a transaction which indicates a transfer of $50 from account A to account B. Read operation here means we are trying to recover the data from hard disk to the main memory, because unless and until the data is read to the main memory, it cannot be updated further. Then the ALU operation subtraction is being performed. A is equal to A minus 50. A is the data item in terms of DBMS on which the operation is performed. So account A is the data item for DBMS. On first, the read operation happened, then we deducted the amount, and then we performed the write operation. So whatever are the things written in the bold, they are the operations, and whatever are rest are the instructions in which ALU operations are required. So write operation is you are trying to update that data item to the hard disk. So it is similar to that of the save. When we save a document, actually it gets written on the hard disk from the main memory to the hard disk, so that when the machine is restarted after a shutdown or maybe a power failure, the data, whatever was saved in the hard disk, can be retrieved through the read operation again. So that is the meaning of write operation. Then again, we read the data item, we perform arithmetic addition operation that we transfer $50. That means we are adding 50 to the B account, and then again we are saving the data item B. That means we are writing the operation onto the hard disk. Now in this transaction, what are the main issues we face is we face major issues like failure in terms of hardware or maybe system crashes. The second type of issues we deal it with concurrent executions of multiple transactions. Now, concurrent means they are happening one by one. There is one single processor, but there are multiple requests at the same time. But we do it one by one since the processor is only one. But the instruction being carried out in such a microsecond that we feel that simultaneous operations are going on. Simultaneous means at the same time, but it cannot happen in terms of one processor, because at a time one processor can do only one job. So what is the difference between concurrent execution and simultaneous operation is, in concurrent operations we try to manage multiple requests in such a way that the waiting time is less and the person assumes that his activity or job was carried out immediately. Whereas in simultaneous transactions, actually the transactions are happening at the single instant. So if you want simultaneous operations, then we want if there are 5 operation requests at the same time, we should have 5 processors also. But in concurrent operations, it does not necessarily mean. So pipelining is the concept which is adjacent to the concurrent operations, because in pipelining, for example, in operating system, if a process is being executed, another process can go into the ready state. So if there is a running operation happening on A item, B item can be prepared for ready state. Ready state means the resources, whatever is being required for A item, it is being prepared. Okay, so simultaneously we feel that ready and ready operation is being performed, but actually ready and running, both are performed simultaneously using different resources. But if it is using the same resource, then definitely we need to have that type of resource in multiplication. Okay. Going to the next slide. What are the required properties of a transaction? So we have 4 properties named as ACID, ACID. A stands for atomicity. So atomicity means either the transaction should be null or full. Null means nothing should happen. Full means if it happens to the fullest. So if there are 6 instructions given earlier with example transfer $50 from account A to account B, okay, either if there is a power failure, say after third instruction, so either the instruction shouldn't be performed at all, because it should not happen that $50 has been transferred from account A, but it does not go to account B. This will be something which is blunder. So if it is happening after 3, then better it should be null. Okay, or if it is happening that all the 6 transactions should be happened, that means 6 instructions should be happened, then we say that the transaction has been performed full. So atomicity, again I'll repeat, either the transaction should be full or null, but it should not be partially executed. So in the SQL, we perform it by using commit operation. So commit, we write it before the first instruction, and then again we write it after 6th instruction. So commit is nothing but save operation. It is similar to the save operation. So it writes the data onto the hard disk the moment we say save. Commit. So in normal Word document or any other document, we perform save operation. In SQL, similar to save is commit. So the moment we say commit, all the data is saved. Then we start the transaction with instruction 1. When instruction 6 is performed, we again say commit. If suppose transaction failure happens after third operation, since the commit was not performed after third operation, it will directly go to its last commit. That means null. Second type of property is durability. So once the user has been notified that the transaction has completed, the updates of the database by the transaction must persist. So we are using commit operations. That means we are taking care of the hardware aspect, the volatile aspect of the primary memory, and the non-volatile aspect of the hard disk. So if you want to increase the durability, after even commit, we do not know the hard disk can also crash. So we can have multiple copies of the same data, that is called as RAID levels, that we will go in another topics, RAID. So durability is maintained by RAID levels by having multiple copies of that in the hardware also. Next is the transaction concept. Third property, consistency. So consistency is that if we have multiple copies, then also all the copies should be having the same value. For example, if there is a read operation going on the same data item, and T1, T2, T3, T4, all 4 transactions are making use of the data item A. Since concurrent transactions are there, the data item is shared. In terms of parallel systems and simultaneous operations, every processor will have its own memory. Data is not shared. They are being performed independently. But in terms of concurrent operations, they are performed dependently. Distributed system is the example of concurrent transactions. Okay, and in today's world, the most example which we are using pervasive system in our day-to-day life is internet and mobile. They are anywhere, anytime application, and both are the best example of distributed systems. Okay, so if we write a mail in machine A and we try to access it through another machine by again logging it from another machine, we get the same thing, right? So similarly, consistency is being maintained in multiple copies, and that's the best example of distributed system. So if the same data item is being read, then there is no problem. But if suppose simultaneously multiple transactions are trying to write on the same data item, if there are they are writing on different data items A and B on the same time, then there is no problem, because A and B can be independent of each other, being written independently by two transactions. Okay, but if at the same time 4 transactions are writing the same copy on data item A, then there will be a conflict. Okay, so that conflict should not arise. Either one transaction should complete the write operation, then another transaction should start. So that is, if this is being achieved, then we say that consistency is being maintained. So ultimately, a consistency when the sum of A and B operations in our previous example of dollar transfer 52 count A and B, okay, so that is unchanged by the execution of the transaction being run concurrently. So example given here is sum of balances of all accounts minus sum of loan amounts must equal value of cash in hand. So next type of property of transaction, ACID. So I transfer stands for isolation. If between steps 3 and 6 of the fund transfer transaction example, another transaction T2 is allowed to access the partial updated database, it will be seen as inconsistent data. Okay, so the sum A plus B will be less than it should be. So isolation can be ensured trivially by running transactions serially. So what is a serial transaction? When T1 is complete, then T2 should start. It's not necessary that the entire T1 transaction should complete all the instructions. Maybe if you can see over here, the T1 read A is equal to A minus 50, write A. So 1, 2, and 3 instructions, they all are working on the item A. So when all transactions on item A is completed, then the operations of item B is started. Okay, and that is why it is called as the serial transactions. So the asset properties of a transaction are as follows. ACID, A stands for atomicity. The transaction be either null or full, used by commit transaction. Then consistency, the isolation preserves the consistency of the database. All the copies should have the same data item value. Isolation is although multiple transactions may execute concurrently, each transaction must be unaware of the concurrently execute transaction. That means it should be given priority to write that data, finish that data, and then other transactions should start. So for that item, it should get locked, and that is called as isolation. Durability, multiple copies should be kept in case of database failures, system failures. Still the data should be persist. That's why to increase the durability, multiple copies should be maintained. So there are different types of transaction state: active, partially committed, failed, aborted, and committed. So as similar as we have in operating system, we have a ready state, we have a running state, okay, we have a waiting state, and we have got a start state, we have got an end state. Similarly, in our DBMS transaction also, we have got active state, we have got partially committed after the final statement has been executed, okay, but it is still not fully committed, failed after the discovery that normal execution can no longer proceed, aborted after the transaction has been rolled back and database restored to its state prior, and last is the committed state, that means after successful completion. For example, we are trying to upload any video on the YouTube, okay, and there is an internet failure in between. So either we can cancel the upload or we can wait for the connection to establish. So if we cancel the upload, then what it happens, or by through the system crashes and the upload immediately cancels itself, that is called as failed. Okay, when we abort, we try to cancel the upload ourselves, that means we try to kill the transaction, or we restart the internet to start the uploading from where it has stopped. Okay, so similar things which it happens in our day-to-day life. In DBMS, we have got some specific words, and that is called as active, partially committed, failed, aborted, and committed. So this is the diagram. First, it goes to active state. Then it goes to partially committed. If some system failures happen, it gets failed. If nothing, it goes okay, then it goes committed. If after failed, then you have to decide whether you restart from where it had failed, or you can actually kill the transaction. That means that is called aborted. So concurrent executions are nothing but the multiple transactions that are allowed to run concurrently in the system. So what are the advantages? Increased processor and disk utilization that leads to better transaction throughput. So you know the waiting time decreases, but still using one processor itself, you can achieve multiple requests. Second advantage is reduced average response time. Okay, so the waiting time, it decreases. Then what is a schedule? A schedule is a sequence of instructions that specify the chronological order in which the instructions of concurrent transactions are executed. Okay, so 1 to 6 instructions in our previous example, that was nothing but a schedule. So this is the schedule 1, where we will go through our previous example. So this is the example of serial schedule. Serial means in sequence. So the T1 transaction is first completed with the commit operation, and then the T2 transaction starts. So very simple. This is a serial schedule where one transaction completes, then the another starts. Then second is schedule 2. Okay, this is again an example of serial schedule where the transactions are just vice versa. First T2 completes, then T1 is completed. Schedule 3. This is similar to the schedule 1, if you can carefully notice it. But the only thing is, first the transaction T1 on data item A is completed. Then on similar data item A, T2 is completed. Then T1 is on data item B is completed. Then on similar data item B, T2 is completed. But if you can see T1, unless and until the entire transaction is completed T1, T2 is not completed. Hence, it is equivalent to schedule 1. In schedule 1, 2, 3, the sum A plus B is preserved. Okay. So schedule 1, 2, 3 are equivalent to schedule, serial schedule. Schedule 4, this is the concurrent schedule that does not preserve the sum of A plus B. Why? Because T1 on data item A did not complete fully, and on the same data item T2 started. This applied to even data item B also. What is serializability? A possible concurrent schedule is serializable if it is equivalent to a serial schedule. It may be not a serial schedule, but it is equivalent. So different forms of schedule, equivalence gives rise to the notion of conflict serializability and view serializability. So in this, for right now, to simplify, we ignore the read and write operations. So conflicting instructions. Let I and ij be the two instructions of transactions Ti and Tj respectively. instructions II and IJ conflict. Why they are conflicting? If there exists some item Q accessed by both II and IJ. So as said earlier, there will be a conflict. See, if there is a read operation on the same data item as instruction 1 is suggesting here, there is no conflict. Conflict will happen when either one of them is writing or both of them is writing. In either case, there will be a conflict. Okay. So conflict serializability, if a schedule S can be transformed into a schedule S dash by series of swaps of non-conflicting instructions, we say that S and S dash are conflict equivalent, because we try to remove the conflict, okay, by swapping some instructions. And because of swapping some instructions, we try to decrease the conflict and convert it into a serial schedule rather. So here, if you can say schedule 3, okay, it is a non-conflicting instructions. Therefore, schedule 3 is conflict serializable. And if we try to convert into a serial schedule, then it converts it into a schedule 6 as shown here in the figure. So example of a schedule that is non-conflict serializable. We are unable to swap instructions in this particular example, okay, to obtain either a serial schedule T3, T4 or a serial schedule T4, T3. Why? Because there are two write items done by T3 and T4 both. So to solve this problem, we will just try to learn a precedence graph. It is a data structure like you have learned stacks, queues, linked list, trees. Okay, you have learned graph data structure also. So a direct graph where the vertices are the transactions. Okay, that is called the precedence graph. So we draw an arc from Ti to Tj if the two transaction conflict. So precedence graph is generally created, okay, for conflict transactions, and we will later see whether that can be converted into a serial schedule or a not conflict. We may label the arc by the item that was accessed. So how do we test the conflict serializability? A serial schedule is conflict serializable if and only if its preceding graph is acyclic. Cycle detection algorithms exist which take proper n-square time, where n is the number of vertices in the graph. If precedence graph is acyclic, the serializability order can be obtained by topological sorting of the graph as shown over here. Okay, either it can be converted into B figure or it can be converted into C figure. So A, it's a non-cyclic, we convert it into B or C. So Ti, then it goes to Tj. So we can first take this Ti, then we go to Tj, and then we go to Tk, because first this level will complete, then this level will complete, then this level will complete. So Ti, Tj, Tk and Tm. This is nothing but equivalent to the B figure. Second is Ti, then Tk, then Tj and then Tm. So this is nothing but C figure. Okay, so this is the two serializable order converted from A. So we come to the recoverable schedules. If a transaction Tj reads a data item previously written by the transaction Ti, then the commit operation of Ti must appear before the commit operation of Tj. Because if commit operation does not happen, okay, before the Tj transaction reads the data item previously written by transaction Ti, if it is not committed earlier, then probably Tj will be accessing a corrupted data, or maybe which is not saved or which is not updated data, rather we should say. Okay, so that is why first we should commit the data, then other transaction should be allowed to see the data. If other transaction also tries to see the data, the other transaction also can check whether it was committed by the last transaction which updated it. Okay, so the following schedule is not recoverable if T9 commits immediately after the read A operation. Okay, so there should be having a commit operation after this write A in this figure, then the T9 should have read the item A. Okay, whereas there is no problem in read B because read B was not written by both the transactions. So if T8 should abort, T9 would have read and possibly shown to the user an inconsistent database state. Hence, database must assure that schedules are recoverable. Cascading rollbacks. Cascading rollback, a single transaction failure leads to a series of transaction rollbacks. Now, what is a rollback? When we say commit, okay, it is saved, but we can do undo operation. So till when we can do undo operation? Till the last saved. Or what we can do in between the transactions in SQL, there is an option called save point. So we can say save point P, and then we can say after 3 instructions, we can say rollback P1. So it will get undo till the last save point named P1. Okay. If P1 is not mentioned and just rollback is given, it will go to the last save point. So rollback is nothing but similar to the undo operation. So cascading rollbacks, if T1, T10 fails, T11 and T12 must also be rolled back as given in this figure, can lead to the undoing of a significant amount of work. Now, cascadeless schedules. For each pair of transaction Ti and Tj such that Tj reads a data item previously written by Ti, the commit operation of Ti appears before the read operation of Tj. This we discussed already, but we say that this as cascadeless. Every cascadeless schedule is also recoverable. Why it was recoverable? Because it was committed. It is desirable to restrict the schedules to those that are cascadeless. So example of a schedule that is not cascadeless here, because it was aborted. Why? Because the commit transaction was not performed in between. If the commit operation would have been performed here, okay, after the T10 write A, okay, and after the write A of T11, then definitely T12 would have been able to retrieve the updated data. Concurrency control. A database must provide a mechanism that will ensure that all the possible schedules are both conflict serializable and it is recoverable and preferably cascadeless. It's not always possible that it would be cascadeless, but it should be preferably cascadeless. So a policy in which one transaction can execute at a time generates serial schedules, but provides a poor degree of concurrency. So every time if we will go for serial schedule, if one gets completed, then we will start. So it will not be a concurrent schedule then. Okay, we are trying to maximum get the throughput of our CPU and all the resources that we have. So we should be able to justify the concurrency. So a serial schedule is just a most simple type of concurrency. But if you want to go the higher usage of concurrency, then you should be able to solve it through conflict serializable, recoverable, and cascadeless issues. So concurrency control schemes trade off between the amount of concurrency they allow and the amount of overhead that they incur. Testing a schedule that serializability after it has executed a little too late. Okay, so the goal is basically to achieve to develop a concurrency control protocols. And what are those? Conflict serializable, recoverable, and cascadeless. Why? To assure basically serializability. So this is our goal for concurrency control. So there can be weak levels of consistency. Okay, so where it can be weak, where the schedules are not serializable. So by default, a transaction is expected to have the level of consistency as serializable. Then you can have a repeatable read. Repeatable read means multiple transactions are reading the same copy. So you should make sure that only committed records are being read. Third category is read committed. Only committed records can be read, but successive read of records may return different values. So they can be read different values. Say may data item A can be read, data item B can be read concurrently likewise. So lower degrees of consistency useful for gathering approximate information for the database. Warning, some database systems do not ensure serializable schedules by default. So we need to incorporate all the protocols of concurrency, to maintain serializability. Okay, to convert them into conflict schedules, to recoverable schedules, and preferably cascadeless. So as told earlier, in SQL, what are the instructions which you can use? Commit and rollback. There is a set auto commit on. So there is a set auto commit on. Okay, so in JDBC connection, set auto commit on is set to false. But by default, you can set it to on also, so that whatever transactions you are doing, it should be saved. But if you are doing something like transferring amount 50 from one account to the another, then you should better keep this option set auto commit in Oracle as off, okay, as false or maybe off. And then whenever you start a transaction, say commit, and then when you end the transaction, say commit again. So view serializability, let S and S dash be two schedules with the same set of transactions. So S and S dash are view equivalent, okay, if three conditions are met. First is if in schedule S, the transaction Ti reads the initial value of Q. Then in schedule S dash also, the transaction Ti must read the initial value of Q. So if you go through all these three instructions, the three conditions, it actually means that it should be a replica. Okay, a view equivalent means it is a replica. A view you can understand, like if there is a drawing, there can be an upper view, a side view, okay, a top view. So they are ultimately the same object, but they are different views. So we can create multiple copies of the same data, that is called views, and then run concurrently. So a serial schedule S is view serializable if it is a view equivalent to a serial schedule. So every conflict serializable schedule is also a view serializable. Below is the schedule which is view serializable but not conflict serializable. Why? Because it is not the exact replica, right? The T28 is not reading the data item. It is immediately doing the write operation. So it is not view serializable. Okay. That is why it is not equivalent. And why it cannot be converted into a serializable serial schedule? Because to convert it into a serial schedule, it should have the similar operations. Okay, so since this is not view equivalent, it cannot be even converted into a serial schedule. So every view serializable schedule that is not conflict schedule has blind writes. So blind write means before reading the item, it writes the data. This is called blind writes. So if you have got blind writes in your schedules, then you can without any hesitation say that it is a serializable schedule, conflict serializable schedule, which cannot be solved. Okay, and which cannot be solved, that cannot be a view serializable. So how to test a view serializability? You create a precedence graph test for conflict serializability. Okay, that cannot be used directly to test the view serializable. So whatever precedence graph we used, okay, that was to convert it into a conflict serializable schedule. But as we said earlier, that every view serializable cannot be a conflict converted into a solved as a non-conflict serializable schedule. Hence, precedence graph test would not be here. So for this, you need to create that problem into a N-complete problem, which is a topic of the DA, that is Design of Analysis and Algorithms. So when that subject would be taught, probably then we can actually go for testing of the view serializability. So you can ignore this point right now. So this is another example, okay, that it is a serial schedule T1 and T5, yet is not a conflict equivalent or view equivalent. So you can go through this example as well as a practice. And this ends the topic of transaction.